So in the first two sections of Unit 4, we have learned how to approximate the value of an integral, a definite integral, by either using like a Riemann sum, a midpoint approximation, a trapezoidal approximation. We've also learned how to do this geometrically when our function is something that we can graph and find the exact area between our curve or line and the x-axis. And then in section 2, we also learned how we could use the definition of a definite integral to evaluate a definite integral. And we might remember that that was particularly tedious. So really, beginning in section 3, the way that we will most often evaluate the value of a definite integral is by finding the antiderivative. And the antiderivative is referred to as the indefinite integral. So these two words, or phrases rather, antiderivative and indefinite integral, we could think of these as one and the same. So if I think about a function, like when we take the derivative of a function, that is an operation, right? I know the derivative of f is f prime. The derivative of f prime is the second derivative of f, or sometimes I say f double prime. So there has to be a way to go backwards. So how could I go from my second derivative to my first, or from my first derivative back to my function f, or from my function f to its antiderivative, which will often use an uppercase f, a capitalized F, to represent the antiderivative of lowercase f. So we could think of the process of finding the antiderivative also as an operation. So if we consider, and I know these examples are on page 51, if I consider the derivative of x squared, I know that that would just give me 2x. So when I find the antiderivative, notice that the indefinite integral does not have limits of integration. There's no a and b. My antiderivative of 2x should therefore be x squared. However, what if I consider taking the derivative of x squared plus 2? Well, the derivative of x squared plus 2 is 2x. So wait a minute, because now it seems like the antiderivative of 2x should be x squared plus 2. If I consider one more case, if I take the derivative of x squared minus 3, well, I still get 2x. So it seems like the antiderivative of 2x should be x squared minus 3. Notice all three of these antiderivatives we got, they're the same in that we have an x squared, but they're different by a constant. Our constant on the first one was just 0. So we call that the constant of integration. So there are infinitely many antiderivatives of 2x. So the antiderivative of 2x generally is x squared plus c, where c could represent any constant. C could be 0, c could be positive 2, c could be negative 3. Since I know that taking the derivative of a constant, I get a 0. So it's really, really important that anytime we're finding an antiderivative, or anytime we think about evaluating the indefinite integral, it's really important that we always add a constant of integration. All right, so the properties of indefinite integrals, these first two properties are the same as properties of definite integrals. When I'm taking the indefinite integral and I have a sum or a difference, I can integrate term by term. So I can integrate f and g and then add them together, or f and g and then subtract them. And then similarly, when I have a constant, I could pull it out, find my antiderivative, and then multiply by the constant. So all of the indefinite integrals in this box, and these aren't all of the ones we're going to learn, these are many of the rules we're going to learn. These are all rules that we are going to need to memorize. But a lot of them, we're going to know them already because we're just working backwards from how we take a derivative. So if I look at the constant rule, for example, I know that when I take the derivative of a constant times x, I just get the constant. So going backwards, if I integrate a constant, I get the constant of x plus c. Similarly, if I think about the power rule, I know that when I take the derivative of a power, whatever my exponent is, I'm going to like pull it out front and multiply by my exponent, and then I'm going to subtract 1. So if I did that with this example, I would pull my n minus 1 out front, and I would multiply, or sorry, n plus 1. I would multiply that with 1 over n plus 1, and then I would subtract 1 from my exponent. That's just going to get me x of n. So working backwards, when I'm finding my antiderivative, I'm going to add 1 to my exponent, and I'm going to divide by my new exponent. That rule looks hard. Like when you look at it written down, it looks confusing, but that's something we're going to do a lot, and you'll be plenty good at it. All right, in the next section, these are all antiderivative rules we know based on the derivative. So for example, I know the derivative of sine of x is cosine of x. So when I integrate cosine of x, I get sine of x plus c. I know the derivative of tangent of x is secant squared x. So if I ever integrate secant squared x, I get tangent of x plus c. Where we have to be careful is that unlike our derivative rules, the sign, S-I-G-N, like positive or negative sign here, is much easier to mess up because, for example, the derivative of sine is positive cosine, but the antiderivative of sine is going to be negative cosine of x plus c. So a tip, like something that always works for me, is to write down my antiderivative. If my antiderivative is a cofunction, then it's going to be negative because I know when I take the derivative of a cofunction, there is a sign change. S-I-G-N, sign change, not S-I-N-E, sign change. So again, we just have to be careful with the positive and negative signs. And again, we're going to memorize these rules. So I would strongly recommend making flashcards and being able to study these along with our derivative rules until we feel like we've got them down. All right, finally, this last group, the last 6 rules at the bottom, these are again all rules that are based on our derivative rules. So I know the derivative of the arcsine of x is 1 over the square root of 1 minus x squared. So the antiderivative of 1 over the square root of 1 minus x squared is arcsine of x plus c. So again, we just need to memorize these rules so that we know them literally forwards and backwards. Okay, then there's 2 things I really want to point out that are important. This rule, when I integrate 1 over x, I don't get the natural log of x plus c, but I get the natural log of the absolute value of x. And if I think about it, the domain of an antiderivative should match the domain of its derivative, of its function. So like the domain of the function 1 over x is, well, I shouldn't say equal sign there. The domain is that x cannot be 0, but x could be negative numbers. However, if I find the domain of the natural log of x, not only can x not be 0, x cannot be negative. So to fix that, if I put an absolute value around the natural log of x, now my domain is the same. So my domain is that x can be positive or negative numbers, just not 0. And to get into why this works like in greater detail, we'll talk about that at a later date, why we get the right value when we plug in the absolute value of x instead of just x. But for now, we could think of that as relating back to its domain. And then the same time, we're going to see that one more time when we think about arcsecant. So when I take the derivative with respect to x of the arcsecant or inverse secant of x, we get 1 over the absolute value of x times the square root of x squared minus 1. So similarly, when I take the antiderivative, you'll notice that the absolute value is in the arcsecant function. And if you want, we can get into more detail about why that is later. But for now, just be aware of those 2 because it's actually pretty important. All right, so to try some examples, this first one, we're just finding the antiderivative of a polynomial function. So we're just using this power rule. And again, the idea here is that we're going to just add 1 to our exponent and divide by our new exponent. So if I start with my first term, x to the fourth, I'm going to add 1 to my exponent, and I'm going to divide everything by my new exponent. So I get 1/5 x to the fifth. My next term, 2/3 is a constant multiple, so it just comes along for the ride, or negative 2/3 rather. When I get to my x cubed, I'm going to add 1 to my exponent, so 3 plus 1 is 4, and divide by my new exponent. All right, when I get to 3x squared, I'm going to add 1 to my exponent, divide by my new exponent. When I get to my negative x here, I could think of that as like negative x to the first power. I'm going to add 1 to my exponent, making that a 2, divide by my new exponent. And then again, when I get to my constant, I'm going to multiply that by x, because the derivative of 5x is 5. So the antiderivative of 5 is 5x. Now finally, we've got to remember our plus c here. So we could leave our derivative like this. I might clean this up. I might think of this as 1/5 x to the fifth minus, let's see, 2/3 times 1/4 is going to be, what, 1/6 x to the fourth plus 1x cubed minus 1/2 x squared plus 5x plus c. All right, in that second example, my favorite antiderivative rule is my favorite derivative rule. The antiderivative of e to the x is just e to the x. And when I get to this next piece, 3 secant squared x, well, the 3 comes along for the ride because it's a constant. The antiderivative of secant squared x is tangent x. And then I cannot forget my plus c. All right, the next example, if I integrate this, again, I can do this term by term. Also, I want to point out that while there aren't parentheses here, we could write them here, but it is the general convention that an antiderivative starts with the elongated s symbol and ends with dx, our differential of x. So when we're writing an integral, definite or indefinite, we need to remember our dx. So when we start and stop that way, the parentheses or the grouping is implied. So it's okay that we didn't write parentheses here. All right, so we are going to use our rule. We said that when I have a power with a base that is not e, I'm going to get 3 to the x times 1 over the natural log of that base, or just I could think of that as divided by ln of 3. And then when I get to 2x to the fifth, I can use my power rule. So I'm going to add 1 to my exponent and divide by my new exponent. And then negative sine of x, we want to be really careful here. The antiderivative of sine of x is negative cosine of x. So subtracting a negative, we're going to get a positive there. So if I clean this up just a little bit, I have 3 to the power of x divided by the natural log of 3 plus 1/3 x to the 6th power plus the cosine of x plus c. All right, try this last example. Pause the video and hit resume when you're ready to go. Again, g, capital G, that's going to represent the antiderivative of lowercase g. So this is really, if I'm finding g of x, this is just asking me to find the antiderivative of 3 over x squared plus 1. And remember that 3 is a constant multiple. It comes along for the ride. I can even pop it out to the front if I want, using the constant multiple rule up here. Just looking for where that rule's written down. So if I have a constant multiple, I can pull that out. And I could think of this as 1 over x squared plus 1 dx. And I will recognize that that is arctangent. So I know that the derivative of arctangent of x is 1 over 1 plus x squared, or x squared plus 1. So we end up getting 3 times the arctangent of x plus c. All right, so antiderivatives can be challenging at first because we are now going in a different order, like our brain is working backwards, and it's easy to kind of get stuck going one direction, finding a derivative versus an antiderivative, but we just need, like anything else, to practice this a lot. All right, so here's some good news. There's not a, well, it's sort of good news. There's not a product rule or a quotient rule for integration. Don't worry, there are some other rules we're going to learn after this, but we don't have to know a product or a quotient rule. So when we are asked to take the integral of a product or a quotient, we have to deal with that product or quotient differently. And we'll learn some other methods, like there are some things right now that we could not integrate. Like at this moment, we could not integrate x times the sine of x, because we don't have a rule for that, but we will learn other ways in the future to deal with stuff like that. What we can do, though, is we could eliminate the multiplication or division. So in this first example, we could eliminate the multiplication by distributing x to the 1/2 power to x squared plus 1. So really, what I'm going to integrate is going to be, let's see, x to the 4 halves. So I'm going to integrate x to the 5 halves power plus x to the 1/2 power. So all we did was distribute the square root of x to both of those terms. So now, using our power rule, I'm going to add 1 to my exponent. So 5 halves plus 2 halves is 7 halves. Divide by my new exponent. Remember, dividing by a fraction is the same as multiplying by its reciprocal, so that's times 2/7. And then x to the 1/2, when I add 1 to that, I'm adding 2 halves. So I get x to the 3 halves times 2/3 plus c. So each time I've got to remember my constant of integration there. All right, in this next example, we are asked to find capital F, which is again an antiderivative of f of x. So in order to do that, I just need to integrate x squared minus 3 over x. Again, though, we don't have a quotient rule. So I could deal with this a couple ways. I could do like division of polynomials, but what would be easier is to just split the terms in my numerator, kind of uncommon denominate. So I know that this is the same as x squared over x minus 3 over x. And I could rewrite that as x minus 3 over x. Okay, so what we're really integrating here is x minus 3 over x. All right, so now I know in my first term, x, I'm just going to use my power rule. I'm going to add 1 to my exponent and divide by my new exponent. And when I get to that minus 3 over x, I could think of that as minus 3 times 1 over x. So that 3 comes along for the ride. And I know the antiderivative of 1 over x is the natural log of the absolute value of x. So we get 1/2 x squared minus 3 ln absolute value of x plus c. Do not forget the plus c. Because sometimes we have to find the constant of integration. So far, all of the antiderivatives we found, if they have a plus c in them, those are called like general antiderivatives. Sometimes we need a specific antiderivative. And this will happen a lot when we are solving differential equations. That's something we're going to do a lot later in the semester, but a differential equation is an equation that involves a derivative, so it's nothing to be scared of. All right, so in this next example, we are asked to find the antiderivative of f of x that passes through the point 1, 5. I want to point out that 1, 5, that is not a point on the function f. F of 1 is not 5. That is instead a point on the antiderivative. So f of 1 is 5. And remember, like 1 is an x value, 5 is a y value. I know you know that. All right, so when we find the antiderivative passing through this point, what we're going to find is a specific or a particular antiderivative, because we said there are infinitely many antiderivatives of lowercase f of x. So let's start by finding the general antiderivative. So f of x is going to equal the indefinite integral, or the antiderivative, of 3x squared plus 2x minus 1. So again, just using the rules we've learned, I'm going to take my 3x squared, I'm going to add 1 to my exponent and divide by my new exponent. For 2x, I'm going to add 1 to my exponent, divide by my new exponent. When I get that -1, that constant, I'm going to multiply that by x, and then I'm going to pick up my plus c. So right now, I have that capital F of x is x cubed plus x squared minus x plus c. So again, we said that this is called a general antiderivative. But we want to find the specific antiderivative that passes through the point 1, 5. So I just need to plug 1 in for x and 5 in for f of 1. So my output is going to be 5. That should be 1 cubed plus 1 squared minus 1 plus c. So I'm just plugging in 1s for all my x's, and that should equal 5. So 5 equals 1 plus 1 minus 1 plus c, which is 1 plus c. And if I subtract 1 from both sides, 4 equals c. So our specific antiderivative that we're looking for is x cubed plus x squared minus x plus 4. So we said that 4, that constant, could be any number, and this would be an antiderivative of lowercase f, our function f of x. But if I want this antiderivative to pass through this particular point, c must be a number that causes the antiderivative to pass through that point. The next example is worded differently, but it's asking us to do essentially the same thing. So we are asked to find y equals f of x. We are told that that is the solution to the differential equation y prime equals 2 over x plus x squared, satisfying f of e squared equals e to the power of 6. So I know that if my derivative of y is y prime, if I'm going from y prime back to y, I'm finding the antiderivative. So we'll talk about this much more later, but when I solve a differential equation, my solution's an equation. All right, so to find y, we need to integrate y prime, which means we need to integrate 2 over x plus x squared. So the antiderivative of y prime is just y. The antiderivative of 2 over x is 2 times the natural log of the absolute value of x. The antiderivative of x squared is 1/3 x cubed. And again, we still have a plus c. So again, we call this the general solution. So if we were just asked for a solution to this differential equation, this would be our general solution to the differential equation. And any constant we plug in for c is a solution. But we're instead asked to find the specific or particular solution that's going to satisfy this point. And so since y is f of x, I need to plug in e squared for x, and my output should be e to the 6th power. So like this is the ordered pair that should be on my solution. So like on my solution curve. So I know e to the 6th should be equal to 2 times the natural log of the absolute value of e squared plus 1/3 e squared cubed plus c. All right, so, whoops, that was e to the 6th. Well, the natural log, well, first of all, e squared is a positive number, so I could drop the absolute value in that last step. The natural log of e squared is just 2, so 2 times 2 is 4. And then this becomes 1/3 e to the 6th plus c. And when I solve for c, if I subtract 1/3 e to the 6th from 1 e to the 6th, I should get 2/3 e to the 6th. Subtract 4 from both sides, I get c. So this is our c value. I'm not going to bother with common denominators on those two terms, but that's our constant that will cause our solution to our differential equation to pass through the ordered pair e squared comma e to the 6th. So our final answer, we call this the particular or specific solution. I'm just going to add my c value. So 2/3 e to the 6th minus 4 is my c value. So like this would be, again, our particular or specific solution. We'll hear that language a lot with differential equations. All right, if you'd like to pause the video, try this last one on your own, or if not, I'm just going to cruise through it. So again, we are finding h of x, and it is the antiderivative of 2 secant squared x plus secant x tangent x, and it's going to satisfy this ordered pair 0, 3. So again, that's a point on our antiderivative, not a point on h of x. So we have to find our antiderivative. Well, this 2 comes along for the ride. I know the antiderivative of secant squared x is tangent of x. When I get to my next term, the antiderivative of secant x tangent x is secant x. And then I pick up my plus c. So then over here, I want to find c by plugging in. We often call this our initial condition. Should have mentioned that before. So I want to plug in my initial condition, or my given condition here. So if h of 0 is 3, that means 3 equals 2 tangent of 0 plus secant of 0 plus c. Oops, sorry, that was my laundry timer. All right, we know the tangent of 0 is just 0, so 0 times 2 is 0. The secant of 0 is 1, and so I get that 2 equals c. So again, to write my final answer here, our solution, h of x, is 2 tangent of x plus the secant of x plus 2.